Hi, I am Sam, your teacher, Sam, my teacher, Sammy, teacher. Take a look at this series of numbers being added together. If this series goes on forever, do you think it's possible to reach a definite answer? Well, let's look at the pattern first. It starts with 8, and you add 4, which is half of 8, and you add 2, which is also half of the previous term, and the numbers are getting smaller and smaller. But however small they become, if we keep on adding numbers forever, isn't the sum going to get bigger and bigger, even though the growth will be slowing down? We can actually visualize this operation using figures, so we're going to do that right now. Let's say we have a square, and the area of the square is 8. It could be 8 squared centimeter, squared inch, or whatever. Now, let's add half that area next to it. So you're adding a rectangle with area 4, and you add half of that rectangle, which is a square with area 2, a rectangle area 1, and half of that, area 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. If we keep doing this forever, since the upper right corner will be filled eventually, we will be adding another square with the same area 8 to the original square that we started with. Now, let's put the numbers and the images together. We started with the first term, 8, this area, and multiplied that number by 1/2 to find the next term, which is 4, and we added the number, and the area increased, and we multiplied the new term by the same number to find the next term, which is 2, and we added that number also, and the area increased a little bit more, and we did the same thing over and over infinitely, each time adding on the half of the previous term. And as we continue adding more terms, this corner right here will eventually be filled, which can be described as the first square came from the first term, which is 8, and the new square added to it, which is the sum of all the other terms, and it turned out to be the same area, and the combined area is 16. There's actually a name for this kind of series of numbers, and the name is an infinite geometric sequence. In any infinite geometric sequence, you start with the first term, and you multiply a certain number. Let's call the number r. So now you have the second term, and you add it to the first term, and you multiply the last term by r again, and add that term to the whole thing, and the pattern continues infinitely. Now, when the number you multiply each time is greater than -1 but smaller than +1, you can actually find a definite sum of the infinite geometric sequence, and there's even a formula for that. That formula is sum equals the first term of the sequence divided by 1 minus the value of r, which is the number you multiply each time to find the following term. And for the example we used, the first term was 8, and you divide that by 1 minus 1/2, because that was the r value that we multiplied each time. And since the denominator 1 minus 1/2 leaves 1/2, we can rewrite this as 8 over 1/2. And since 8 divided by 1/2 is the same thing as 8 multiplied by 2, 8 times 2 will be 16, which is the sum of the infinite geometric sequence. And that's the same number we had when we were visualizing the sequence by finding the area. I hope you found this idea interesting, and I'll see you next time.